talking today about the last part of our fuzzy inferencing mechanism component, which is one of the most important part to provide us with the decision signal within a particular system. And this particular area is quite important in this description of fuzzy logic system. And remember, in the previous slide, we have spoken about the notion of defuzzifier. So we spoke about aggregator last time. We spoke about fuzzification of signals. We are talking about fuzzifier this time, where we are going to see how defuzzifier, where we are going to see how to create out of an aggregator type of signal. We are getting some meaningful type of signal that is going to become the input to an actuator or the input to a certain type of device, because device do not work with the fuzzy type of current or fuzzy type of voltage. So the aggregator, the fuzzy signal, provides us with the overall representation of the information that we are looking at, but the defuzzifier is going to provide us with the knowledge that we would like to extract, which is going to become the part of the decision signal that is going to generate for the actuator or the controller or the device itself. So that's what we are going to study during this hour. And this is one of the last major components for our system as we are describing it. So let me start here by saying that there are many types of defuzzification. So defuzzification is the reverse of what we have seen earlier last time in the last lecture in the form of fuzzification. Remember fuzzification, singleton fuzzifier, we spoke about it in the last lecture. This is the reverse action of what we are trying to do. So the control action, as I just mentioned, need to be a crisp type of function. So it needs to be a voltage, 0.4 volt, 5 volts, to activate a certain type of device. So we are going to see three major, type of defuzzification techniques, and possibly more. There are many more in the literature. A number of them are described in chapter 3 of the textbook that I have posted in the slides, which are, on Learn. So the method of defuzzification that I'm going to speak about, so the centroid methods, the mean of maxima methods, and the threshold method. So let's start with the most, intuitive one, which is the centroid method. So what is the centroid method? So let's suppose that we have a membership function that we have found to be, of this particular format. So this is the outcome of the aggregator. So this is the results of the aggregator after we have combined all the information from various type of inference engines. So as you can see that this is not the usual type of membership function, but because this is composed of an aggregator function could be also of this particular format. So because, it's aggregated as the results of several type of inference rules from which each one of them we have concatenated them. So this is the outcome of that particular type of results. So suppose that the membership function of the control inference is given by mu cc. So this is mu cc, okay, or this one is mu cc here, okay. And there are two ways for computing. So the first one is given by the continuous case, which is the center of gravity of that particular membership function. So basically, when we are going to compute the membership function, we are going to have various type of membership functions. So here, let's suppose that we have a membership function. This could be the results of a membership function. This could be the results of another membership function similar to this. So let's suppose that this is, originally this way, and this is originally this membership function, but because we are aggregating them, we are only seeing the continuous aspect. So what we do, basically, we take this part here, membership function here, we take, its membership function here. So this is an integral value, as you can see, and then we compute its values for C. So we are integrating the value of C. C is basically the variable of the universe of discourse. So this is the variable C. So this is the variable C, and this is the mu C. So this is the mu C. So what we have here, we have, a variable for the first one here, okay? So this is the C. So we are integrating this trapezoidal format over this particular C. And then we divide the same thing under the area of this mu CC for this particular support system. And we do the same thing for this one, okay? So what we are doing here, so we have the C integrated with the mu CC. We can also do, a straight type of integration over this particular type of shape. So we can do it over this particular type of shape, and then we do the integral of this particular shape over all the elements from C, over the universe of discourse for all these particular representations. So we can do it this way, we can do it this way. So this, we can integrate all these particular function, and you can see here, so this is the variable C here, and this is the function of mu C, okay? So what we can do, we integrate the function of C mu CC, so divided by the integral of the membership function itself without its multiplication by C. So the usual case of the centroid method is a little bit complicated, so you have to find the center of gravity of all these particular area. That's why we call it centroid method. So the centroid method is the more difficult type of representation for this system. And it is quite difficult because we have to integrate all these membership function times the variable C, and then divided it by the whole area of mu CC. So this is the continuous case for this particular representation. There is also the discrete representation where we are integrating the values of Ci with respect to mu CCI. So when we are dealing with two or more discrete values for the system, with representation for Ci is being the value of that particular value over the universe of discourse time the value of the mu C, Ci. So where you are dealing with particular values for the representation here. So in the discrete case, so we have this particular element. So what we do, we take the maximum value that is reached by mu C at the value of C1 here. So this is C1, this is C2, this is C3, okay? And this is mu C1, and this is mu C3, okay? So what we do, we compute first the product of C1 times the maximum that the membership function reaches, and this is mu C2, okay? And then we add the summation of C2 times mu C2 plus C3 times mu C3, and then we divided it by all the values of mu Ci, mu C2, mu C3, which are these type of components values that are taken by the range of, the maximum value of the membership function. So this is the discrete case, and this is the continuous case for the center of gravity. So this is the centroid method, and it is the more accurate, but it's the more difficult to compute. There are other aspects that people have utilized in the area of discrete or continuous systems to obtain the value for the membership function. So let's suppose that our membership function in the case of a continuous case is given by this particular membership function for the aggregated values. Okay, so one way for using it, so this is, we call it the unimodal type of representation of the system. So for the control version is unimodal. So this is also a unimodal type of representation of a membership function. Unimodal because we have one single value that takes a maximum type of value. All the other ones are values that are shaped out in as the value of the membership function. So in this particular case, what is the value of the membership function here? The mean of maxima. So the maximum value is going to be given by the value which is represented by the maximum. So the value, so this is C max, it's the maximum value that is reached by the membership function at this particular element. So Cmax, where the membership function gets its maximum, is going to be given by the control value. That's where the peak of the membership function is being taken. So sometimes we have some other type of representation. So sometimes we may end up with something of this nature, for instance, okay? And then another mode here, and then something like this, and then another mode, okay? So in this particular case, we have what is known as the multi-modal. So this is one mode here. This is another mode of the membership function. This is another mode of the membership function. So the function takes several type of modes at its maximum. So simply what we do here, so we do extend the version there, and we find where the maximum of these values of these modes are occurring. Okay, where do they occur? And then what we do, we simply take the values of where they are occurring. So this is C1, this is C2, this is C3. Okay, so what we do, we multiply C1 by the maximum value of corresponding to C1, then plus C2 times the maximum value where C2 occurs, then plus C3 where times the maximum where it's occurring. So this is the summation here, and then we divide that. We divide this value by the sum of where these membership functions have taken place. So it's mu I, it's mu2 here, it's mu3. So this is mu1 here, this is mu2, and this is mu3. So as you can see from the form of these particular type of values, usually we are obtaining a representation that is over the universe of discourse, because here you can see we are dividing the mu i's. It's multiplied, it's true, by ci's, but we divide it by a value in the form of mu i's. So ultimately, this is, leading us to a dimension of the value that is over the universe of discourse of that particular membership function. So this is what we call the multimodal membership function. So when we are dealing with multimodal membership function, this is what we are, what we should be obtaining in this particular representation. So here I don't know what is this delta, so this should not be there. But that's, possibly it means that it's the range, the maximum range where this part of the membership function is taking its maximum. So that's the mu1, the mu2, the mu3, and it could go on and on for p numbers. So when we have one single unimodal, that's the value where the maximum occurs, and that's the control value, that's the defuzzified version. If we have several type of multimodal values, then we do this particular operation for this particular type of representation for this system. So this is what we are trying to do. And as you can see, this particular representation for this continuous case is similar in shape to the one that we discussed in the earlier slides, where we have Ci times mu Ci divided by the maximum of the values of mu Cci for the discrete case of the centroid method. So the discrete case for the centroid method is no other than the same as the values that we are computing here for the system for a continuous case, but for multimodal type of version for the system. So this is what we call the mean of maxima, and for unimodal system and for multimodal system. Sometimes it may be desirable to leave out the boundaries of the control inference membership function. What does that mean? It means that sometimes, so let's suppose that this is the aggregated membership function, and sometimes we would like to disregard these particular type of region from our control version. So what we do, we take, so we would like only the core version of this particular membership function. So we would like to have, without diluting the value of the control system, we are going to utilize an alpha cat for the membership function itself. And then the alpha cat is going to provide us with the membership function of this particular form. So we take an alpha cat, which is going to be representative of all these particular representation. And then we take the value for all the remaining version of the interval. So let me go here. Let's look at here. Let's look at this particular type of version. So this particular version here, so we are cutting the function, so by an alpha cut, and the alpha cut, as you know, I mean, so we take an alpha here, and then we take the alpha cut. So the membership function value at the alpha cut, so this is represented in this particular region, and then we do it in this particular way, and this represents what is known as the threshold type of value. And we compute exactly as we have done for the centroid methods, and we disregard there the area which is minimizing, I mean, or related to very, very low values of the membership function. So we only take the value of the membership function that counts the most, which is this particular representation of the membership function. So this is known as the threshold method. This is not very much used in the literature, but still some people have utilized it. So they are using the alpha cut of the system. So it's a modified alpha cut if you look at it this way, but nevertheless, we utilize the alpha value where the membership function is, I mean, located, I mean, for all the values that are upper than alpha. And then we take the support set of that particular alpha cut or the interval of the alpha cut, and we fill it up as well, similar in this particular formats, and then we take the defuzzified value. Again, this is not very much used, and it's rarely, I mean, used in textbook or even in articles, but there are some researchers who have utilized this. So whenever you hear the threshold methods, this is what it means in this particular way. So this is another way for computing these particular type of values for the membership function. There are other representations, I mean, that are known as the bisector of area. So what is the bisector of area? So if you take again a membership function of this particular format, so this is the aggregated, again, this is the aggregated membership function. So the bisector of area, it means it's the location where you have the value of the area from either the sides of this particular element here. So this is the value of bisector of area. So it is the coordinates of the membership function over the universe of discourse of this aggregate function, such as the area in this location from the left of the bisector of area and from the right of the bisector of area are equal. So that determines the value of the center, the bisector of area. So mathematically speaking, it's the mu, which is the membership function. So this is the mu C of C. So the integral, so again, this is an integral from alpha. So this is alpha to CBOA, okay, is equal to CBOA to the value of beta. Okay, so that particular value here, which makes the two integral equal, is known as the bisector of area. Okay, and alpha is the minimum of the C, which is the support set, and beta is the maximum of the membership function itself. So this also has been utilized in the literature. It's a value that is given here, which determines, I mean, the two type of areas that become equal to each other. There are easier values that people have utilized, where we take the what is known as the smallest of maximum. So let's suppose that this is a membership function, okay? So the maximum of this membership function here occur at this particular type of value, okay? Which has a value of, I mean, at this particular level here, okay? Okay, so this value is known as smallest of maximum. And this particular value here is known as largest of maximum. So what it is the coordinate at which the membership function has the smallest value. So you have a membership function here, so this is mu C. So its smallest value for the maximum value is known as the smallest of maximum. So these usually occur when the model value of the membership function is not 1 point, when the model value of the function is several type of points. Remember here in the area of the multi-model representation here, so this is unimodel with 1 point, with multi-points here, and we were able to create the maximum. But what happens if we are dealing with model values that are values constant? So we utilize the smallest of maximum, we utilize the largest of maximum, okay? We can also utilize something else. So people have utilized this as the middle of the maximum. So the middle of maximum is known as where that maximum value is taking place. So it is taking place at the SOM plus LOM divided by 2. This is the mean of the maxima. So this is another way. So this is the mean of maxima when the function has a model value that takes maximum over wide range. So we have here smallest of maxima, first one, second one, largest of maxima, and third one is the mean of maxima. Okay, so the mean of maxima is also something that we are utilizing here when the value of the modes is not one single point, okay, and when the membership function is continuous in this particular case. So these are some of the areas that people have utilized in dephasification. So we have seen so far 6 or 7 of them. So let me give you an example here to give you an example for this particular membership function. So this for this particular value for this system here. So here is, and I would like to rectify this particular slide. So this is actually, it's the smallest of maxima, and this is the largest of maxima. So please rectify that part. So that is one error in this particular graph. So let's look at these type of representation. So you see that this membership function, which came out of an aggregated type of procedure for this particular system, and it provided us with this particular shape or with this particular shape. So it could be this one or it could be this one. So this is example 1 and this is example 2. So the centroid of area, the most difficult one to obtain, as I mentioned to you, is by obtaining the area times the coordinates of the universe of this course here, okay, divided by the area of the whole triangle. So it's basically the center of a gravity of that particular area, and that's, I showed you the formula on how to utilize it. The other part is we have seen the smallest of maxima, and this is the largest of maxima. So this is, we have seen it in this smallest of maxima and the largest of maxima. So the smallest of the value where the membership function take its maximum value, that's SOM. This is LOM. So all of these could be values, and their values are, what are they? Are this. They are here. And the value for the centroid is also here. So always remember the value of the control or the dephasified version is what is, where is that value, mathematical value is located. For the largest of maxima, it occurs at -2. Smallest of maxima, it occurs at -8. For the centroid of area, it occurs at -3 for this particular example, or -3.4. And then we have the bisector of area. So what is the bisector of area? It's that particular coordinates, which is located here, where the area from this region is equal to the area from this region. That's the bisector of area. And then the last one is the mean of maxima. So what is the mean of maxima? So we take this particular area here, not this particular area, this particular interval where the function reach its maximum value, and then we divide. So we use SOM plus LOM, largest of maxima, divided by 2. So that's where that MOM. So this MOM is no other than that particular location. Okay, so all of these are defuzzifiers and they have been utilized in textbooks. So I would like you to understand what they mean. So here we have, this is mentioned correctly, smallest of maxima. This is the largest of maxima. This is the mean of maxima. As you can see, it's in the middle of this value and this value and its coordinates. It's located here. Okay, and then the bisector of area, it's the value of this particular coordinates where the area here is equal to the area here. And finally, the centroid of area, it's the center of gravity of the over yellow area for the system. And I have shown you as well how to compute it. I do not expect during the quiz or during an exam, I mean, of short duration, to ask you to compute a centroid of area because it is a little bit complex. So you have to do that integration. You have to collect the interval for that particular shape of that membership function. So that's what I wanted to share with you here for all these particular type of defuzzification. So defuzzification, again, let me repeat, defuzzification is no other than the extraction of a crisp signal out of the representation of the aggregated function. So you have the aggregated function. In this particular case, it's the yellow area. How to extract an information out of the yellow area? So the question that you may ask yourself here, there are all these type of representations. I mean, which one is best to use, when to use it? So this is my answer to you. The best one to utilize it and the most representative and the most logical that has insight of representation of all this particular area is the centroid. The centroid, where it is located in terms of its coordinates, is the best representative of this particular yellow area here or here. But the centroid is usually a complex value to compute. So what we do, the smallest of maxima and largest of maxima are usually not utilized seriously by people who would like to have a significant insight on what's happening, because it gives you only one information about the maximum value, one information about the maximum value. So which one do you choose, LOM or SOM? People have used both as long as you use them consistently with a particular problem. But a representative of them is the mean of maxima. So the mean of maxima is one that people utilize. So this is the, I mean, one of the other options. So the centroid is one option. The mean of maxima is another option. The bisector of area is also another option, but it is also difficult to compute. Bisector of area is as difficult to compute as the centroid, or less difficult. Okay, so usually people, what they do, they use the mean of maxima for their representation. So basically what they do, they take the maximum value of the system and they utilize it so that they compute that particular value. In case that the representation of the system is not very much complex and you are able to create the centroid of area, then I mean you can utilize it, and it is not very difficult when the shape of the membership function is not very, very complex. So that's what I wanted to share with you about these defuzzification. So far we have seen fuzzification, I mean how to fuzzify a membership function. Okay, fuzzify. And then we have used the defuzzification as well, defuzzify. So that's the reverse of the fuzzification representation. So now, going back to that type of representation now, so if I go back several slides here. So now we have been able to fuzzify an input from crisp to fuzzy. We have seen how to create the, I mean, the rule base, which is the engine K, the aggregator type of signal, which we have seen last set of slides and last lecture, how to create from several type of fuzzy inferencing. So that's the aggregator system. And then the defuzzifier, which is the latest version that we have seen now, which is, I mean, the centroid of area, the mean of maxima, the largest of maxima, the smallest of maxima, which is giving us the value of the decision signal of the model. So that decision signal of the model, ultimately, it's what we are injecting as a crisp value for an actuator, for a motor, for a system that we would like to activate, or for the steering control system of a car or anything like that. So that decision need to be crisp, and we can only crispify it using the defuzzifier type of representation. Okay, so that's basically what we have seen for this particular system. So now I would like to speak about various type of inferencing systems that have been utilized in the literature. So there are few of them that have been utilized in the literature. And that inferencing system, what does that mean by inferencing system? Inferencing system is no other than this way for getting the aggregate signal. So the aggregate signal of the outputs of the fuzzy system is what is known as the inferencing mechanism. So that's what is known as also the fuzzy system, basically the fuzzy inferencing. That's what we have seen in earlier slides. So there are three of them. Okay, so there is Mamdani fuzzy model, there is the Sugeno fuzzy model, and then the Tsukamoto fuzzy model. And each one of them has been utilized, I mean, a lot in the literature over many, many years. I'm going to speak about the Mamdani one and also about the Sugeno fuzzy model, because they are the most used type of fuzzy models. The Tsukamoto fuzzy model also could be utilized, but it's not very much used in the literature and in applications. Why? Because this is, I mean, a problem related to the form of the fuzzy membership function. But it is mentioned in the slides, but it's not going to be included, not included in the quiz, not included in the quiz, okay? In the quiz. So although it is mentioned here, but it is not part of the quiz. In the quiz, actually. Not included in the quiz here, not fuzzy. Okay, so let's talk about them. So how they do aggregate and how we create this particular aggregator value. So once we create the aggregator value, as I mentioned a few moments ago, then we are able to defuzzify the output of the system. So let's go back to what we have seen earlier when we have used the max-min operator for the aggregation part. Remember, this is rule 1. This is rule 2, so this is an example where we have multi-antecedents. So we have X, we have Y, and we have Z as the consequence. We have X, we have Y, and we have Z as a consequence. And this is the context. So this is the input variable. So the input variable could be a fuzzy membership function, or it could be a singleton fuzzy membership function, as I showed you earlier. So in this particular case, it's a green version here, to showcase you that the input is a fuzzy representation of an input, okay? So let's look at the first rule. So the first rule tells us if A1 and if B1, then we have C1. So that's the first rule. The second rule tells us if A2 and B2, then we have C2. So as if this is the temperature, if temperature here is high and humidity is low, then you have air conditioner is high. So if temperature is very high here and the humidity is somehow high with another membership function representation, then the air conditioner is somehow low. So these are the representation for this particular system at this particular stage. So what we do, the first thing that we do, we project these type of values, okay, these membership functions. So we have A prime here, B prime here. So as you can see, I reproduced them here. Okay, I reproduced them here. Okay, and then what we do, we take basically the area here of the intersection, degree of validity of A1 and A prime. And then we take the degree of validity of B1 and B prime. And then simply we take a T norm. We have seen that the T norm, the default T norm, is going to be the minimum operator. So what we do, we take the minimum of this value here and the minimum of this value here to obtain what is known as the firing strength. So this is the firing strength we have defined last time when we spoke about fuzzy inferencing. And that firing strength is projected on the output of the first membership function. And we have seen how that particular effect is going to impact this membership function. So now we have a clipped version of the original membership function, and its maximum value, it's the minimum value, which is the firing strength of the first rule. We do the same exact thing for the second rule, and we obtain that our firing strength is here, is the value of omega-2. And then we clip this particular membership function, and it gives us this blue type of representation here, this blue type of representation. And then what we do aggregation. So we do the aggregation and we take the max. So the mean operator here as applied to the version of these particular, these type of things is applied. So the mean is the T norm that we are selecting. And then we aggregate here using the max. Okay, so the max type of operator here is going to be applied for this membership function. And the max operator here is going to provide us with this profile of this membership function here, as you can see. So this is the output membership function of what we have obtained. So this is similar to what I showed you in the set of slides that we have seen since the start of this particular lecture for today. Okay, so it is usually it's a clip type of version of certain type of membership function. Sometimes it gives us even some weird type of representation of membership function because we are aggregating clipped version of these membership functions. So this now is the membership function, which is the aggregate of the outcome of all the membership function representation, and it is given by the C prime. Okay, so C prime is going to be the overall value. So the C prime 2 is due to the C2, which is the clipped version. C prime 1 is no other than the clipped version for the, the rule 1 function of our system. So this is the membership function, and then we take the maximum. So it's going to give us, membership function of this particular form in this particular area here. So this is our C prime membership function, and it is this particular area that we would like to, from which we would like to create either the centroid of area, SOA, or bisector of area, or other type of defuzzifier. So we are utilizing the defuzzification over this membership function, which has resulted from all these type of rules that have been computed in this particular type of representation. So this is the max mean operator. Why we are using the max mean? So the max in the form of the max of all the things that we are clipping. So here, so we have this clipped here, and then we concatenate them. We aggregate them using the max operator. And the mean operator is no other than the operator that we select for this particular firing strength. This is the value that is going to generate the signal that is affecting each clip part of the rule. So this is very, very important to do. We have seen here 2 rules, R1, R2, but we could have 16 rules. We could have 100 rules. We could have thousands of rules. And we use exactly the same formulation that we have utilized here. Okay, so this is one representation for the Mamdani fuzzy model. So let's look at this particular example. So let's suppose that we have here fuzzy sets A, and the consequent is given by B. Okay, so we have an entity here. We don't know what is this entity, but we say that if X is small, then Y is small. If X is medium, then Y is medium. If X is large, then Y is large. So we have all these, rules that we concatenate with each other. So this is our engine. This is the K knowledge engine that we have created before. So now we have several representation of each element of the antecedent. So we have the medium, we have the large, and we have the small. Okay, so we would like to obtain the output of the system using the Mamdani fuzzy inferencing model. And we would like to utilize the center of area as the fuzzification operator. So the system is telling us here, create this particular surface or create this particular curve that is going to be utilized as a guiding type of process for extracting a control signal for this particular system. So that's why we call it fuzzy inference system here. So we are trying to get some fuzzy inferencing decision system here. So fuzzy inferencing system. So from several type of rules, rule 1 here, rule 2 here, and rule 3 here. Okay, so let's look at this particular system and let's look at this particular representation. So here I have concatenated all the rules. So this particular thing here, we can do it in this particular manner. So the first rule is that if x is small, so this is x is small, which is the blue, then y is small. Okay, so then y is small. Remember that x and y, as you can see, are over two different universe of discourses. Remember, so this is the antecedent, this is the consequence. Okay, so this, I mean, so the x is small. The second rule is going to be if x is medium, so we are departing for the medium now, then we have y is, it's difficult to, I mean, type on this type of PDF files, not type, better draw on this PDF file. So then we have medium. So this is medium, this is small, this is small, and this is x, this is y. Okay, so these are universal discourse of the consequent, this is universal discourse of, so this is of the antecedent, this is of the consequent. And the third one is going to be if x is large, okay, then y is large, okay, and the large of y again is over different universal discourse. So basically what we did, we have amalgamated all these type of rules here into one single figure. Okay, so this is one single figure for the antecedents, and this is for the consequent. But the blue here, this is related to this. The medium here is related to this, and the large here is related to this. Okay, so the same thing here, the small pertains to this here, the medium pertains to this one here, and the large pertains to this large. Okay, so we would like to extract some information here out of this particular system. So what we do in general case, because here the system doesn't tell us the value of the input, so we are going to apply it for all the input range of x, which is from the value of -10 to 10. So from -10 to 10. Okay. So what we are going to do here, we take only, I mean, I will take only one example here to showcase you what we are doing here. Okay. So at this particular level, so let's suppose the value is going to be, let's say, -8. So -8. Okay. And it applies -8 here as well. -8. Okay, so -8 here is going to be fuzzified here. And when we do the -8 intersection with this particular membership function, we found the maximum value here. So the maximum value here provide us with firing strength, which is equal to 1. What does that mean? It means that we are exciting all this membership function in totality. For the value of -8, it happens to be further than, so as you can see, -8 is not exciting the green, it's not exciting the large. So here the value -8 is the fuzzy value, -8, so it doesn't have any intersection with the membership function here. And then we have 0 here and 0 for this particular value, because -8 doesn't excite, it doesn't intersect with any membership function of the input values. Okay, so for the value of -8, for this particular instance, we have only this membership function. And this membership function, so if we express it here, so it's going to be the aggregate. Okay, so the aggregate membership function for this particular -8 here, we have to extract and find its center of area. So the center of area happens to be in this particular value of the output. Okay, so this particular value of the output is going to be what is the control effort for the system when it is subjected to an input value at -8. So this is an example on how to utilize fuzzification, using singleton fuzzifier, utilizing the aggregation, and then the defuzzification. Okay, so this is the aggregation. So we have combined all of them, but only the first one is going some representation of the membership function. So this is the aggregate membership function, and this is the center of area, and it gives us the center of gravity for this particular value, and that's the value for the decision-making process. So this is what we want to say in this particular type of representation for this particular system. Okay, so let's look now for all the values that are between -10 and +10. So we have a representation that we are dealing here at this particular level. So we have from -10 to +10. As you can see, from -10 to -6, we don't have any effects other than the first output membership function. And then we have the values -6 to -4 here. And this basically pertains to two clipped membership functions. The same thing here for this region here. It's going to be one clipped membership function, and the third one is the third clipped membership function. So this is a 2D representation between the x-axis and the y-axis for this particular representation, and this is what is known as the control surface. So this is what we wanted to mention in this input-output curve, and this is the single input Mamdani fuzzy model. I see that we have here, I mean, one student has joined me, although I'm recording this this lecture asynchronously. So, but Tian, you can ask questions if you would like. I mean, I'm recording this on Saturday, and this is going to be posted for the students, and it is supposed to be the lecture of Monday. So this is an asynchronous lecture, but feel free to ask since you are attending this lecture here. So the Sugeno fuzzy model is another type of fuzzy inferencing system. And this fuzzy inference system is very special in the fact that it doesn't require a particular value for the processing of the output. So as you can see, this fuzzy Sugeno fuzzy model, which was discovered in the 80s, and it has been used in a number of application and implementation. So what the system provides us, it doesn't provide us with the membership function, it provides us rather with the function of the input variables. So it is a function of the input variables. The function could be x plus y. It could be x times y. So it's a function, it's an explicit function. So if your output of the system is basically a system that provides you with a representation of your model, then your system is going to be provided in this particular format. So this is rule 1 here. This is rule 2 for the system. Okay, so it says that if x is equal to a1 and y is equal to b1, which is our membership function here. So all of here, we are talking about fuzzy sets. Then the outcome, the consequent, is going to be a function of the variable x and y. For the second rule, it's going to be another function of f2. And we can go on and on and on for many type of rules here. But for the description of the rules, for the outcome of the rules are going to be described in this particular type of formats. They are functions. So what this system provides us, it's going to provide us with much better representation in the form of avoiding an ad hoc representation of the decision signal, which is going to be a crisp signal. Remember that the defuzzifier component is a crisp signal that we need to compute in order to implement for physical type of system. So this system, as we are going to see in the next slide, is a system that provides us with the representation of this particular format. So here, an example of the output is going to be constant. So the constant, it's going to be called zero order model. First order model is where we have first order polynomial representation of the system. So the overall output aggregation is obtained through a weighted average. Let's look at this particular weighted average. What does that mean? So let's look at this Sugeno fuzzy model. So let's look similar to the example that we have seen. If the variable here is small, it could be temperature is small, we don't call temperature small, then the output is going to be a function, first order polynomial 0.1x plus 64. Second rule, we have a second function. Third rule, we have a third function. So these are not going to be fuzzy membership function as we have seen in the Mamdani model, but rather they are going to be polynomial of zero order, first order. They could be also of higher order polynomial. Let's look at what we are trying to achieve here. So this is the system. So this is the antecedents. Okay, this is the antecedent. So these are the membership function of the antecedent. If x is small, small is a membership function. Second one is medium. Third one is large. Then the consequent is given by this particular format. So as you can see here, we don't have membership functions at the consequence. It is a function of the variables, of the input variables that we have utilized for the system. Now, because this system is powerful and because it's difficult usually to find this particular function, however, the defuzzified value is going to look like this particular form. What are these parameters omega 1, omega 2, omega 3? So for each one of the intersection with the fuzzy singleton here, so let's suppose this is a fuzzy singleton, this is the input, fuzzy singleton here as our input, one single input here for this fuzzy singleton. Look at the intersection here. So the degree of validity or the firing strength, because we have only one antecedent, is going to be omega 1. So omega 1 is the firing strength for these particular values. For these particular values. Firing strength, by the way, is equal to degree of validity if we have one single antecedent. So firing strength or degree of validity are equivalent. Once we have more than two antecedents, as I'm going to show you in the next example, then we take the firing strength. So now what we are doing, simply what we are doing here, we know the value where the X value has been applied, and we look at the omega 1, the omega 2, the omega 3. For each one of them, we compute the Y1. Of course, the Y1, we are able to compute it because we know the value of X. So the X here, what is this value of X? So Y1 is known, Y2 is known, Y3 is known, omega 1 is known, omega 2 is known, omega 3 is known, and this gives us all the values, and it gives us a crisp value here without having to do recourse to center of area, or to bisector of area, or to the largest of maximum, or to the smallest of maximum, or to the mean of maximum for creating defuzzified value. So the defuzzified value here is immediately generated from this particular type of representation. Let's look at this system when we are using, I will go back to this particular representation here. But let's look at when we are dealing with two antecedents. So now we have two antecedents, and this is a consequence. Two antecedents and one consequence, and two antecedents and one consequence. So we have here four rules for our eyes. Okay. So what we do, we exactly do the same thing. So omega 1 Z1 plus omega 2 Z2 plus omega 3 Z3 plus omega 4 Z4 is going to provide us with this particular value. So what does that mean here? So if we are expanding this into this particular representation here, so we find the firing strength for all these particular values. If X is small and Y is small, then we find omega 1 here. We find the firing strength for X is small and Y is large, then we obtain omega 2. Then we find for X is large and Y is large, and then we find omega 3. X is large and Y is large, and then we find omega 4. And this could apply to any value of the X. So X here could be any value, Y could be any value, and we obtain for each one of them the omega 1. And what we obtain for this particular X and Y values, we obtain for each pair of X and Y, we obtain a value for the Z, because we have the Z1, the Z2, Z3, and Z4, which are extracted from this particular type of representation. So this is one way for computing the Sugeno-Fuzzy model. So now if I go back to this particular part here, so this is the X is small here, and I put them under one single graph. The 2 is small, the Y is large. So here what we have, so we have here, I mean, if we dislocate all of these particular values, so we have here the X is small, we have the Y, the X is medium, and then the third one is the Z, the third one, which is the large one, large membership function. So what we are doing here, so all these are the three rules. So now to generalize what we have seen in this one here, so X is no longer going to be one single fuzzy singleton, so we are going to take it for all the universe of discourse, from this value here to this value here. So for each one of them, we are going to compute the value of Y, and that's what we are doing here. Okay, so we start with X is equal to -10, and then we compute for the system what is the value of X minus 10. So then we take the value for, I mean, the X minus 10. So does it excite the second one, the third one when it is in this particular area? It doesn't. So for X minus 10, we are only finding a degree of validity that is going to excite only the first function, because the second function, omega 2, is equal to 0. The third one, omega 3, is equal to 0. So only the first one is going to be excited, and then we implement the X as value of 10, and then we compute the value of Y. So this is exactly how we are extracting this input-output version. So for X value, each one of the values, we have the Y value. So if we have -6 here, so then we have to extract the -6 and what is its representative value of Y, and then we obtain what is known as the overall input-output curve of the fuzzy rule. Okay, if it were crisp type of rules, we obtain system that is not, I mean, so as you can see, that is not differentiable here. For a system that is fuzzy, we have very, very smooth transition between various type of points for the system. So this is what is known as the Takagi-Sugeno type of representation, which is the Sugeno representation, where the output of the system is not a membership function, as you can see, but it's a function of the variable. The difficulty with this particular model, of course, is the fact that it is very difficult to obtain this particular function. But for people who have expertise in this particular system, they are able to extract this particular function. Once you extract this particular function, such as here in rule 1, rule 2, rule 3, rule 4, then the system becomes extremely easy to implement. So to recapture what I just said, so there are two types of defuzzification or fuzzy inferencing system. So there is the Mamdani one. The Mamdani one, we use the fuzzy inferencing as we have seen it originally without any problem, but the issue is on the defuzzification process of the model. Defuzzification process of the model, because we have to compute, remember, that centroid of area. And as I mentioned to you, the aggregated membership function of the system is usually complex to obtain. So because of that, then we are utilizing a system that has, a better defuzzifier, such as the mean of max or the centroid, the bisector of area, or the largest of maxima or the smallest of maxima. So here, the difficulty is on obtaining the representative of the outputs of the consequence in terms of a function of the variable. So you can see here, to obtain this particular first order polynomial, it's difficult. It's not easy to do that. But once we obtain it, and there are means for automatically obtaining this using a combination of fuzzy logic system and the neural network, and they don't tackle it in this particular course. So I usually discuss and implement and teach this particular function representation in the graduate course components of this course on computational intelligence for the advanced value. But as you can see here, while the difficulty in obtaining this function, look how easy to obtain the defuzzified function of the system, because once we have the degree of strength, the firing strength of the system, degree of validity for one single antecedent, then we are able to obtain all these particular type of parameters. And if we look at this particular system here for the two membership functions of the antecedent and two membership function of the consequence, we obtain a system similar to this, utilizing these particular type of rules, very, very simple rules that we have defined here. If x is small and y is small, then z is minus x plus y plus 1. If x is small and y is large, then z is equal to minus y plus 3. So here, let me show you one particular rule here, and then you can extrapolate for all of them. So here we have two antecedents. So let's take rule 2. Okay. So we have x there and y there. And then the consequent, which is z, is equal to minus y plus 3. That's the second rule. Okay, so rule 2 here. Okay, so this is the x universe of this course. This is the y universe of this course. And as you can see, the x is small here. So let me check here the small. So x is small here, so it's mentioned here like this. And y is large, so it is expressed in this particular form. Okay, so for instance, at a particular element that we select in this particular area, we fuzzify, and then we see the element here. So this is omega 1, the degree of validity. But let's look here whether we have a degree of validity with the second version. So let's suppose, so this is for x1 and this is for y1. So let's suppose that we take this pair of x1 and y1. So the y1 pair here doesn't intersect with this function. So we have only one degree of validity, and this is now going to be applied to the firing strength. So then what we are going to utilize in this particular representation, so this is, for this particular rule, so we have here, so this is, this is omega 2, so this is rule 2 here, okay? So this is rule 2 here. So the firing strength for rule 2 is given by omega 2, and then given that y here is not being excited, so y is going to be equal to this particular value of the y. But what we have here, we are going to have omega 1 z1 plus omega 2 z2. So the second rule is going to be given by omega 2, which is the maximum value here. So omega 2 is equal to 1 here. So we have the largest value for omega 2. And then z2 is going to be equal to y2 here, that is applied. So this, yeah, again, this is y2 here. and this is x2, this is rule 2, okay, for this particular level. So we have z2 is equal to minus y2 plus 3 here. So the y2 here, which is located in this particular region, and we find it this way. So we don't have any type of excitation related to the first type of rule. So if we are utilizing this particular scheme here, so we detect omega 2 for here. We also try to find omega 1 for the first rule if it applies to it, and we can see that it applies to it, and then it also applies for the y is small, and then we try to find the degree of firing strength here. So here the firing strength is given by omega 2, which we found it here. So we expand exactly what we have seen for rule 2 for all the rules that we have in the representation of this particular system. And then we compute omega 1 z1 plus omega 2 z2 plus omega 3 z3, omega 4 z4. So omega z2, for instance, z2 here is equal to minus y2 plus 3, okay? And then we multiply it by omega 2, which is equal to 1. So this is for one particular rule, and we expand it for all the rules. Once we do this for all the values for x between minus 5 and 5, and for y between minus 5 and 5, we obtain this particular control surface for the two input Sugeno-fuzzy model. It's known as the input-output surface, okay? And this is one way of creating the input-output surface. So why this input-output surface is very important? So what we can do in real-world application, instead of crunching all these type of rules every time we go through a fuzzy system, we simply have this particular surface on which we have to spend time to create it. And then once the sensor measures a particular value for x and the particular value of y, then it's going to go to that particular surface and it's going to inject that element for the decision surface. So it doesn't need to do the Sugeno-fuzzy model for each one of the values of x and y values. As soon as the system extracts a value for the sensing for x and the y, then we utilize what is known as the 3D control surface. 3D control surface. So this 3D control surface is no other than a surface that provides us with a lookup table, lookup information that is going to help us out with that particular type of representation. Okay? So that's what I wanted to mention. So the Tsukamoto model, I mean, in the difference of what we have for the other systems, is that the membership function of the output is an open membership function. It is similar to this particular type of representation, is known as monotonic type of mapping. So I am leaving it there. I mean, for looking at it, it's not going to be part of the system, but you can use it. It's very similar to the Mandani type of representation, and the only difference is that the fact that these output of the system, the mapping is monotonic. So for you to know about it, Tsukamoto fuzzy model is a system for which the output membership function is of monotonous type of representation. Okay. So I'm not going to go over that example. So let me go finally over one room comfort control system. The next lecture, by the way, it's going to be a simulation of a problem that is similar to this one. Possibly this particular problem is going to be simulated for you. The next lecture might be given by one of my TAs who is going to record it and leave it for you for the Friday lecture of next week. So let's suppose that we have the temperature and the humidity, which are the process variable within a particular type of room. So we have a particular room here, and we would like to have an air conditioner for this room. Okay, so there is an air conditioner that is attached to this particular room. So the air conditioner here is using, a fuzzy system. So the air conditioner is going to generate either cold temperature or heat. And this, you have two types of sensors here. So there's temperature, and we have another type of sensor, which is the humidity. Okay, and both of them are going to be sensors that are going to go to a fuzzy knowledge base system, and this knowledge base system is generating, I mean, a decision signal for an air conditioner system. Okay, so this is the model here. So there are two type of sensory values, and this is the fuzzy logic system here. Okay, fuzzy logic system that is going to be connected to an ACE, which is connected to, I mean, a room control system that is going to generate cool or heat for this particular system. So this type of sensor system are provided to the fuzzy controller, as I mentioned to you. So this is the fuzzy logic controller. We call it usually FLC, okay? And it's going to go to the air conditioner. So the fuzzy logic controller determines the cooling rate that should be generated by the air conditioning units. So this is exactly what I just wanted to mention to you. So this is the room temperature sensor, humidity sensor, going to a fuzzy logic controller, heat, temperature. The cooling rate is going to be generated here, and this cooling rate C is going to go to the air conditioner. So the air conditioner is going to be the one that is going to generate cool air or hot air using this fuzzy logic controller. So this fuzzy logic controller requires fuzzification of the heat, of the humidity and the temperature, and it's going to be defuzzified to provide the cooling rate for the air conditioner system once it is defuzzified. So temperature level T, so we are going to check two values for it. So high value, and low value, which denotes high and low. Humidity level also, this is, I mean, humidity high, it's going to be high and low. And then we have the membership function of T are quite different from those of H because they are two universes of discourse. Remember, we have here two universes of discourse. So we have temperature, we have humidity, and we have the cooling rate of the system. Okay, so this is what we have. So this is the rules that we are going to express in the next few moments. Okay, so these are the temperature possibilities, both of them, and these are the membership function of the output system. So as you can see here, the high and low are fuzzy sets over universal discourse. So this is universal discourse humidity, this is universal discourse of temperature. Here, this is the changing cooling rate. So this is the output of the system that should go ultimately to the air conditioner. But ultimately, from that particular output, we have to tune up and create a defuzzified type of system. Okay, so these are the rules that we have for this system. So rule 1, rule 2, rule 3, rule 4. Okay. And this and if here, okay? So this is and if. So the rule 1, it says if temperature is high and the humidity is high, then cooling rate is positive high. If temperature is high and the humidity is low, then cooling rate is positive low. If temperature is low and the humidity is high, then cooling rate is negative low. If temperature is low and the humidity is low, then the cooling rate is negative high, which means here heat. Okay, so when air conditioner is negative, it means that it is generating some heat. So let's look at this particular fuzzy inferencing for this particular system. For a particular temperature, which we are choosing here, and for a particular value of the humidity, which is given by 90% here for 0.9. Okay, so this is, I mean, for the temperature, so this is 30 degrees. So for one temperature, and for 190% humidity, what are we going to obtain? Okay, for a pair of value. So for the first pair of value, so we should intersect each membership function by the fuzzified value of 30. This is the fuzzified value of 30. Remember that we have to fuzzify in order to have the intersection with membership function value. We have to fuzzify. Okay. The same thing here, we have to fuzzify. So this is very similar to the problem in assignment 2. Okay. And I will ask my student TA to go with you over implementation of the system over on MATLAB or on Scikit. Okay. So let's look at, because here we are hitting the two type of membership function. What do we have here? So look at this value here. So this is omega 1, and this is omega 2. And then taking the T norm. So if I don't mention what is the T norm, so then you take the minimum. So the minimum happens to be omega 2. And it's hitting the membership function here at this particular area. So it is only this area that is going to be excited for rule 1. Let's look at rule 2. You still have omega 1 here and omega 2 here. So still the omega 2 is going to be prevalent because we are using the min, max min type of inferencing. Max min. Okay? When I don't mention it, it means that it's the default version. Okay? So this particular value, omega 3 here, is going to give this clipped version. And we continue with the third rule and the fourth rule. Now, we are going to aggregate all of them. Okay, so aggregating all of them using the max rule type of here, we end up with this particular surface area. Okay, as I mentioned to you, this particular type of surface area is complex to obtain the value for the system, and we have to utilize the center of area here to come up with that representative of the center of gravity of this particular area, the centroid. So the centroid is going to be located in this particular region, and it has this particular coordinates. For this particular pair, 30 degrees Celsius, 90% humidity, we have a centroid of area given by this particular value. Okay? So now if we extend, if we go 45 degrees, 90%, it's going to give us another value of the centroid of area. But this Mamdani inferencing model is just to showcase you what we are obtaining for this particular type of system representation. So here in each rule, the lower value of the two grades of the process, so this is the explanation of what I just meant here, the corresponding membership function of C, which is the minimum operation. The resulting clipped membership function of C for all four rules are superimposed. That's the max operation. So that's where the max comes from. Max, min come from this particular presentation. So the aggregation is a max operation. Max operation for all these particular type of rules. Okay, and the mean is the mean of the omega 1 and omega 2 for each one of the rules. So that's the description. This results in a fuzzy set, and it must be defuzzified to obtain a crisp control action. So what happens here, once we have this particular type of action here, the cooling rates, so then the system here ultimately is to be activated, and it's going to ultimately, it's going to generate a value. So this air conditioner now, it's going to be activated by a discrete value because it requires a voltage to activate it. So the cooling rate that is going to activate this air conditioner is no other than a discrete value for that particular system to activate it. Otherwise, the air conditioner is not going to work by receiving the aggregates of the function. And that's why we showcase here the fuzzification part, as I mentioned to you. So this is fuzzification part here, the fuzzification part by singleton fuzzifier, and then aggregate. Okay, so after the fuzzification, then we look at the minimum, so the firing strength, the clip version, and then we aggregate all the values of the clips to find the maximum of the membership function. This is the aggregate function here, and this is the centroid of area to provide you with the maximum value for this centroid function for this membership function that is located here. So this is one example for an air conditioner model which showcase the Mamdani inferencing model for this particular type of representation. Okay, so that's basically what I wanted to showcase you. So there is another example here that I invite you to look at it, and I might invite as well Mahmoud to implement it on MATLAB for you to look how the system is being implemented and how you can implement fuzzy logic and fuzzy inferencing system. And it is going to be recorded for the lecture and the tutorial of Friday. So the lecture of Friday next week and the tutorial is going to be combined into one single presentation, which is going to be the implementation of all these particular values and all these particular representation that I have just shown you. Okay, so this showcase you how to implement fuzzy inferencing, how to implement the various components from defuzzification to aggregation to defuzzification using various type of approaches and various type of techniques. And the example on the room comfort control system should provide you with an excellent example. So this example is taken from my textbook, so you can look at it in chapter 3, and it illustrates even further the description and the representation of these particular type of representation. Okay, so I would like to end the lecture here, and I'm going to post this lecture for the asynchronous lecture of Monday. So there won't be a lecture on Monday. This is the lecture of Monday that I have prepared for you, and please feel free to start looking at it. I'm going to post it, I mean, today for you to look at it, because it might help you as well with assignment, the last problem of the assignments, if you would like to look at it. Thank you again, and thank you for attending these slides and these lectures, and I wish you the best in the preparation for the final quiz and the final assignments, and I will try to post some problems to prepare you for quiz number 3. Thank you again. Have a good day.